We now begin to take a look at quantitative examples involving the conservation of energy, where we have, for example, gravitational potential energy transforming back and forth into kinetic energy. When I went through my quantitative and qualitative lectures in describing potential energy and the conservation of energy, I used the pendulum as a means of conceptualizing the situation. Let's go ahead and turn our first quantitative example into the pendulum situation. Go ahead and copy the following problem down into your notes while I read it to you here. A pendulum has a length of 1 meter. The string initially makes an angle of 30 degrees with respect to the vertical direction. The pendulum is released from rest. In part A of the problem, we'll calculate the speed of the mass as it passes through the equilibrium position. And then in part B, we'll figure out what happens on the other side of the swing when the object comes to rest once again for an instant. In doing so, by using conservation of energy, we're going to begin to describe the oscillation of this pendulum. Okay, now when it comes to drawing out the geometry of the situation, we do so in profile, that is like so. So now this is going to be part A. So right here is our pendulum of mass m and then length L. And then right here, for example, is the vertical direction. This angle right here is given to us as 30 degrees. Okay, right here is the bottom of the swing, like so. That's the equilibrium position. And then therefore, in part A of the problem, if we release the object from rest, we're going to calculate the speed when it passes through the bottom of the swing. Okay, so we're going to release the pendulum from rest. The initial speed here is equal to 0. And then for part A of the problem, if I use another color here, right here is the path that is traced out by the pendulum. It then reaches the bottom of the swing like so. And it does so at an unknown speed v. In doing this, it undergoes a height change. So let's add a little bit of geometry to the situation. Okay, I'm going to go ahead and construct right here a right triangle. This right triangle will be important in just a few moments. But then right here is the height change h. Before I set up our conservation of energy equation, I'm going to go ahead and figure out what the height change h is in terms of the length of the string L, which is given to us as 1 meter, and also the angle of 30 degrees. Okay, the height change h right here, you'll notice is the difference between this value here, which is the length of string L, and this value here, which is the adjacent side of the right triangle that I have constructed. This guy right here, the adjacent side, you'll notice is equal to L cosine theta. So the height change h is equal to L, the length of string, minus then L cosine theta. This is a general relationship that is applicable to situations involving a pendulum. Okay, so h is equal to L minus L cosine theta. Let's go ahead and calculate that value before I go any further. Okay, so in degree mode on my calculator, of course, I now have 1 minus 1 times the cosine of 30 degrees. And ultimately, rounding it off a little bit, the height change here is about 0.13 meters, like so. Okay, now because the energy is conserved, we don't have to do any more dot products associated with the work energy theorem. We can now just employ the conservation of energy expression. So here's the conservation of energy expression as we've seen it thus far, like so. And now what we have to do is fill in the terms, final minus initial, of first change in kinetic energy, and then secondly, change in potential energy. To aid us here on the diagram, you may want to label the following. This right here is the initial position in the problem, and this right here is the final position in the problem. So when I start to fill in the terms, I now do the following. First of all, the change in kinetic energy. We will have a final kinetic energy here at the bottom of the swing with the speed v, so that's 1/2 mv squared. And then minus the initial kinetic energy of 0 because the pendulum begins at rest. Okay, and now we get to this new term, the change in potential energy. All that we have to do is fill in the respective values, final minus initial, of mgh. No more dot products to do. So down here at the bottom of the swing, if we consider this here to be the origin, therefore the final potential energy is equal to 0. And then minus the initial potential energy up here when we start the problem. Once again, this is the initial position. The initial potential energy, rather, is just mgh, where we now know what h is from the geometry from a few minutes ago, like so. And now we just solve for the speed v. Now, in order to do so, I'm going to do an extra step here. I'm going to move the mgh to the other side. I'm going to go ahead and throw away all of my zeros as I do, like so. And then this right here is an expression of the energy transformation that takes place. And we now know exactly what it means. That is, all the potential energy that we start with here at the top of the swing turns into all of the kinetic energy at the bottom of the swing. Recall in the earlier examples that we looked at involving the work energy theorem, I was putting question marks associated with the potential energy terms as we saw them. No longer necessary to do. So now we have right here gravitational potential energy, and that then transforms into kinetic energy at the bottom of the swing. The total amount of energy is a conserved quantity. And now we just solve for the speed v. So algebraically, I'll go ahead at this point and cancel out the mass like so from either side of the expression, cross multiply the 2 to the other side, and then take the square root to get the speed. When we do, we end up with the following expression. Like so, and now we just plug in. So I still have the h here in my calculator from earlier, so times 2 times g, and then take the square root of all of that. And ultimately the speed at the bottom of the swing is about 1.62 or so meters per second. Okay, and now we get to part B of the problem. In part B of the problem, we're going to find the angle made by the string on the other side of the equilibrium position when the mass comes to rest once again for an instant. Now, before I go through the solution, what is the answer? Pretty obviously it's going to be 30 degrees, but here's then how we show that. Okay, so let's set up part B in the following way. So now what we're going to do is start with our mass m and length L like so, and then we're here at the bottom of the swing with an initial speed equal to the 1.62 meters per second that we calculated a few moments ago. And then the end of the problem here in part B will look like this. The object will come to rest here for an instant like so. Once again, let's go ahead and construct the right triangle here. Right here is the unknown angle theta that we're asked to find. And then as the object moves from here to here on my diagram, it once again undergoes a height change. Right here is the height change h. Now, technically speaking, we don't know what h is in this problem. This is basically what we're trying to find. However, once we do find what h is, we can once again use this expression here from the geometry to find the angle theta. In order to find h, however, of course, we just have to set up our conservation of energy equation. And when we do, as you'll see, the terms are basically all backwards. However, to aid us in setting up our expression, let's go ahead and add to your notes here that this is the initial position for part B of the problem, and this right here is the final position. And now let's just go ahead and start filling in our terms, like so. So first of all, we have the change in kinetic energy, final minus initial. The final kinetic energy is 0 because the object ends up at rest. And the initial kinetic energy depends upon the speed v naught of 1.62 meters per second. Now we calculated earlier in part A of the problem. So final minus initial, like so. And now change in gravitational potential energy. Final value of mgh up here, where h is the unknown, minus the initial value of mgh, which is 0, because we start here at the origin in this portion of the problem. So then therefore, final minus initial potential energy looks like this. Notice that all of the terms here in part B of the problem are basically just backwards of what we saw earlier in part A. Let's go ahead and move this term here to the other side. I'll toss away all of my zeros as I do. And then right here is an expression of the energy transformation. It just occurs backwards of what we saw earlier in part A. So all of the kinetic energy at the bottom of the swing turns into the exact same amount of potential energy at the top of the swing. And then at this point, we just solve for h. So let's go ahead and cancel out the mass m, like so. Divide the g to the other side. And then therefore h is equal to the following quantity. If you plug in the numbers, of course, here associated with this problem, we would get the same value of h as we found earlier in part A of the example. It would be once again 0.13 meters. Therefore the angle theta would be equal to 30 degrees. We would then explicitly find that by using this expression here. So as long as there is no friction between the pendulum's string and the attachment, and as long as we ignore air resistance, this then means that this pendulum will oscillate in this manner forever. It will always form an angle of 30 degrees with respect to the vertical direction on either side of the equilibrium position, and the object will always pass through the equilibrium position with a speed of, where is it, right here, 1.62 meters per second. Okay, let's immediately move on to our next series of examples, which involve roller coasters. We talked a little bit about, qualitatively that is, roller coasters back early on in our unit in dynamics. Now in terms of energy transfer, let's examine them a little bit more carefully. And I'm going to do some erasing here. Let's go ahead and get rid of this problem. We've completed it. Like so. Okay, and then let's take a look at the next of our examples involving roller coasters. Let me go ahead and put it here on my screen. Okay, let's read it and go ahead and write it into your notes. A roller coaster cart begins at rest at the top of a hill 20 meters high on a frictionless track. Find the cart's speed as it crests subsequent hills that are 15 and 10 meters high, respectively. So the situation looks like this. Okay, right here is our roller coaster hill initially, and then we have these two subsequent hills like so. Okay, we're given that it's a frictionless track. This then means that the energy is conserved. There will, of course, be a normal force acting upon the coaster cart as it moves through the ride. However, recall that the normal force does no work. So because it's a frictionless track, this then means that the energy is conserved. After I draw out this situation, I'm also going to give you a short primer on the basic physics of roller coasters before we actually explicitly go through the solution. Well, let's draw the situation first. Okay, so here's our coaster cart of mass M. We're going to begin at rest like so. And then we have these three hills. I'm going to call this first hill, Hill A. This is given to us as 20 meters. Let's call this one Hill B, which is 15 meters tall. And this one here is Hill C, which is 10 meters tall. And then what we're going to calculate when we do the problem in just a few moments is the speed here at the top of Hill B. We'll call that VB. And then right here we'll calculate the speed at the top of Hill C. We'll call that VC. So these two are unknown. However, before I do the example, let me give you a short primer on roller coasters. Most roller coasters begin exactly the same way. What is usually the first thing that happens when the coaster train leaves the station? You are lifted to the top of an enormous initial hill. What this then means is that work is being done upon the coaster, usually by a device that is called a chain lift, that then lifts you to the top of that initial hill, thereby giving you a huge amount of gravitational potential energy. You're moving a little bit as well, so you have a little bit of kinetic energy, but by and large, most of the energy that you start with is gravitational potential energy. But then after that, there are no engines or motors or anything like that attached to the coaster train. After that, all that happens is that all of that gravitational potential energy is transformed into kinetic energy and potential energy and so on as you subsequently move through the ride. Of course, there's friction between the coaster train and the track, so some of the energy is lost as heat, but the amount of energy that's lost as heat is usually pretty minimal, at least until you get near the end of the ride. Now, there are some coaster designs that instead of giving you an enormous amount of potential energy at the beginning of the ride, they'll instead give you an enormous amount of kinetic energy at the beginning of the ride. The ride Superman, for example, at Six Flags Magic Mountain. That uses what is called an electromagnetic railgun to give you a huge amount of kinetic energy at the beginning of the ride, but then subsequently all of that kinetic energy is transformed into potential energy as you move up the tower. Another ride that you may be familiar with from local amusement parks is, for example, California Screamin' at Disney's California Adventure. That particular roller coaster does essentially the same thing. That is, it uses an electromagnetic railgun to give you a huge amount of kinetic energy at the beginning of the ride, and then you subsequently transform to kinetic energy and potential energy and so on. Now I'm going to add a little something to this diagram here before we get to the actual problem. Let's say, for example, that after Hill C we have another hill, like so, but this hill is taller than the first hill. Are you ever going to encounter a roller coaster that has another hill that is taller than the first hill if you only have one chain lift at the beginning of the ride? The answer to that question is no, because essentially what I'm illustrating here, if you remember, is Galileo's experiment. So let's start at rest right here at this height, and then remember Galileo's result from his experiment. Regardless of the shapes of the tracks, the object always returned to its original height. So if I release the object from rest here at the top of this hill, and the track is frictionless, this then means that the object will rise to the exact same height like so for an instant prior to moving back down in the opposite direction, because we're assuming here that the energy is conserved. So you are never going to encounter another hill later on in the roller coaster that is taller than the first hill for this reason. However, in order for you to have a hill that is taller than the first hill, what that would then require is an additional chain lift that is built into the ride. This is usually done on roller coasters that have a small scale. Usually engineering multiple chain lifts into a roller coaster design from an engineering standpoint is rather difficult to do, but you will see it sometimes on a small scale. There are a number of roller coasters, for example, at Disneyland that do employ multiple chain lifts into the ride. Space Mountain is an example of this. Big Thunder Mountain is another example. Usually in those situations which occur on a small scale, you can sometimes encounter multiple chain lifts in a ride. But if there are not additional chain lifts in a ride, then you are never going to encounter a hill that is taller than the initial hill. Okay, so that gives us a little primer here on the basic physics of roller coasters. Other than that, it's essentially just transforming potential energy back and forth into kinetic energy as you subsequently move through the ride. Okay, let's go ahead and get back to the problem itself. Now, let me get rid of this original information here, or additional information is not necessary to do the problem. And now we want to figure out the speeds at the top of B and C. Which of the speeds, B or C, is going to be greater? C is, and the reason for that is because at the top of hill C, you are lower to the ground, and then therefore have less potential energy, and then therefore more kinetic energy than you would here at the top of hill B. So we should find that at the top of hill C, that speed is greater than the speed at the top of hill B. Okay, let's go ahead and first of all find VB. I'm going to set up conservation of energy as the object moves from here to here. All right, so let's go ahead and write out our expression like so. And then like I did in the pendulum problem a little while ago, let's go ahead and fill in our terms. So first of all, the change in kinetic energy. So we're going to have here a final kinetic energy with the speed VB, like so. And then minus the initial kinetic energy of 0 because our cart begins at rest. Okay, and then we have changes in gravitational potential energy. Our final gravitational potential energy up here is going to depend upon the height HB. So that's going to be mgHb. And then minus the initial gravitational potential energy up here at the top of hill A, that's going to be mgHa. Like so. And now what we do is we just algebraically solve for the speed VB. So to do so, I'm going to take these two terms and then move them to the left-hand side of the expression. I switch them as I do. So be careful of the algebra. That then looks like this. Like so. So notice what I did here algebraically. These two terms have switched. And at this point, I'm going to go ahead and do a couple of things. I'm going to cancel out the mass m of the cart like so. Here on the left-hand side, I'm going to factor out the g from each term, and then I'm going to cross-multiply the 2 to the other side and take the square root in order to find the speed VB. So take a look at this. After I do those minor algebraic steps, I then end up with this expression here. Notice that this expression here is very similar to the speed expression that we saw in part A of the pendulum problem. The speed of the object is the square root of 2g multiplied by the height change. This will always be the case as long as the object starts from rest. So in the pendulum problem, the object began at rest at a height h, and then therefore subsequently later on in the problem at the bottom of the swing, we found that the speed was the square root of 2gh, where h is the height change. Same thing here. In this case, the height change is from hill A to hill B. So now let's go ahead and fill in the terms. This is 20 minus 15 for a total of 5 meters in the parentheses. So then therefore I have the square root of 2 times 9.8 times 5 meters, and that then gives us a speed of 9.9 meters per second. And now I'll basically do the same process in order to find the speed at the top of hill C. When I do this, it doesn't matter if I set up the problem in going from point B to point C or from, say, point A to point C. It doesn't matter how I set up and solve the problem because the energy is conserved. However, one method of doing so is a little bit easier algebraically than the other. Should I go from A to C or from B to C? I should go from A to C. And the reason for that is because one of my terms, the initial kinetic energy here at the top of hill A, is going to be equal to 0. So if I go from A to C, the expression I'm going to end up with is very similar to what you saw here earlier, except here underneath the radical sign, the height change will look a little bit different. Well, let me just go ahead and set it up from scratch. Okay, so now we're going from A to C. Let's go ahead and start to fill in our terms for the conservation of energy. First of all, the change in kinetic energy. We'll have a final kinetic energy here at the top of hill C. That's 1/2 mvc squared, minus then the initial kinetic energy at the top of hill A, which remember is 0 because the object begins at rest. And then we have change in potential energy. So our final potential energy up here is going to be mghc minus the initial potential energy of mgha at the top of hill A. And then what we do is we solve for Vc. However, take a look at this expression. Notice that that expression that I just wrote down is essentially identical to this expression earlier when we were finding V sub B. The only thing that's different, of course, is that we're talking about hill C instead. So if I go through the algebraic steps, I'm going to end up with the following expression here for the speed at the top of hill C. It's going to be, once again, the square root of 2g multiplied by the height change. Once again, this is always the case as long as the object begins at rest. In this case, however, the height change is greater than it was for hill B. In this case, it's 20 minus 10 meters for a total of 10 meters here in parentheses. So then therefore the speed at the top of hill C is going to be greater than it is at the top of hill B. Okay, so finishing up, I square root of 2 times 9.8 and then times the height change of a 10 meter total. And this ends up being then a speed of 14 meters per second, like so. Okay, there are two more quantitative examples involving gravitational potential energy for us to look at. They are continuations of situations involving roller coasters, but I'll go ahead and I'll do that in my next lecture.